All right. Welcome everybody to our Sept theory seminar. After a little bit of a hiatus, we're picking it up again. And the first speaker of this semester's Sept theory seminar is our own Victoria Gitman, and she's going to speak about Jensen's forcing at an inaccessible. Go ahead.
Okay, thanks, Gunther. And I think this is the first time that I'm giving a talk in the virtual version of this seminar. And this is very exciting because I usually really worry about going over time in my talks. And here, since I'm one of the organizers, I give myself leave to go over time, so I don't have to worry about it. This is one of the perks. So this makes me less nervous than I usually am. And so, okay, so for starters, this is joint work with Cy Friedman. And I'm going to start by reminding people about what Jensen's forcing is, and what it's how it's constructed and what it's good for. And then we will talk about the generalization and why I'm interested in the generalization. So what is the application that that me and Cy have in mind? So Jensen's forcing was introduced by Jensen around the 1970s, and he constructed it in L using the diamond principle. So it's a subposet of sex forcing. So elements are perfect trees ordered by the subtree relation. And it has two key properties which sex forcing doesn't have. It has the CCC. And okay, I don't have the audience view. Gunther, you spotlighted me and now I lost my audience view, but I guess that's okay. I guess you need it for the, so I can kill this.
Do you want me to remove the spotlight? I mean, let's see.
I mean, it's up to you.
This?
So yeah, because then I have the audience view. I just noticed I was seeing myself, and
you should be able to change it on your own machine without needing Gunther to change it.
I don't think so. I think once you spotlight, and also with my Zoom abilities, this will take me the next 20 minutes.
A fair point.
Well, yeah, I chose spotlight for everyone, so that's probably why it overrides what you did.
Yeah, I think so. Yeah, I think that's that. And I really did not want to see myself on the other screen. Okay, sorry.
By the way, since we have already interrupted now, I was just thinking if somebody asked me what is Jensen's forcing, I would probably think of the coding the universe in a real forcing.
I was almost going to say that, but I didn't. Yes, I had in my mind to say that is not Jensen's forcing. So it's the other Jensen. It's what I think I'm the only one that refers to it as Jensen's forcing. But let's just, since I'm going to tell you exactly what it is, the confusion will be cleared up in the next few seconds if it hasn't been yet. But yes, that's exactly right. I was almost about to sort of raise that objection on myself. Okay, so it has the two key properties which sex forcing doesn't have, which is one is the CCC. And this is really one of the key places where you use diamond, because we're going to use it to seal maximal lattice chains. And this other really nice property, which is important for my applications, it adds a unique generic real. So this is something very much unlike, say, co-enforcing, where once you add a generic real, you've added continuum many of them. Here, it's unique. Okay, and even though we usually, so I think no one has ever tried to work with these forcings outside of L, but L is really, if you look carefully at the construction of the forcing, L isn't crucial here, diamond is. You lose something if you don't work in L, but it's not much. And also Jensen gives a particular construction. There are others, there are variables in the construction. So there isn't one such forcings, there are multiple, and I'll point out what those variables are once we get to the construction. But Jensen's particular construction and the fact that he worked in L gives one additional property. And that is that this unique generic real is a pi12 definable singleton, and this is the property that Jensen was really after. We will see that in the applications. But I want to talk a little bit more about this uniqueness of generics property that's associated with Jensen's forcing before we get to the applications. And that is, so you can extend the uniqueness of generics property both to products, to certain products of Jensen's forcing, and to finite iterations. Okay, so this is the notation that I will use throughout the talk. So J is going to be Jensen's forcing. J to the less than omega is going to be finite support omega length product of Jensen's forcing. And J script T and J N is going to be N length iteration of Jensen's forcing. And I'll have something, we really have to be slightly more precise about how to construct this. We will get there. Okay, so Jensen's construction was in the 1970s. The next theorem is going to be from about 10 years ago, I think, approximately. And that's Kanave and Lubetsky's result, extending the uniqueness of generics property to omega length product of Jensen's force. So, and their theorem is in the extension by the omega length product of Jensen's forcing, the only generic reals for J are the ones coming from the omega many slices of the generic filter. So each of the omega many slices, of course, because it's a product, is generic for J, but these are the only ones. So this is the uniqueness of generic for omega length products. And with psi, we showed uniqueness of generics for finite iterations. Okay, so what are the applications? What is Jensen's forcing good for? So Jensen used it to show at the time, because this was many, many years ago, there was a following open question. So because of Schoenfeld's absoluteness, it was known that every sigma 1, 2 definable real has to be constructible. And so Jensen showed that that is optimal because there can be consistently a pi 1, 2 definable non-constructible real. Namely, his example was the Jensen generic in the extension, in the forcing extension of L. So this pi 1, 2 definability was crucial for his applications. Okay, so why did Lubetsky and Kanave prove their theorem? Well, the following became a very popular question on math overflow. So the question was, can you have a countable ordinal definable set of reals without any ordinal definable members? And the question got a ton of upvotes, a ton of comments, and people didn't really know how to answer it. And with this theorem, you have the answer that yes, it is possible. And namely, the set is the omega many Jensen reals in the extension by the omega length product of Jensen's reals. So this is why Kanave and Lubetsky proved their theorem. Okay. And then this is the application that was of interest to me. So let me give a background to this whole thing. Okay, so I was interested in the following question. If you have the second order set theory, Kelly-Morse with the choice scheme, does it also prove the dependent choice scheme? So in order to answer the question, I tried to see what the situation was in models of second order arithmetic, because a lot more work is done in second order arithmetic than in second order set theory. So let me let me explain some of the terminology in the context of second order arithmetic that I just mentioned, and it sort of directly generalizes to second order set theory. Okay, so first of all, in second order arithmetic, one of the hierarchies that you have is based on the amount of comprehension that the theory has. So the weakest theories will have only comprehension for first order, formulas, stronger theories, I have more and more comprehension. And then Z2 is called full second order arithmetic. It has comprehension for all second order assertions. And comprehension is, of course, what kind of formulas define a class. So if you have comprehension for all second order assertion, it means that any second order assertion defines a class. So it turns out that you can strengthen the comprehension hierarchy. So even if you have full comprehension, you can strengthen this further by adding choice principles for classes. And there are sort of two main choice principles that people look at in second order arithmetic as well as second order set theory. And that is the choice scheme and the dependent choice scheme. Okay, so the choice scheme is a principle that says that given a second order formula phi n x, if for every natural number n you have a class witnessing this formula phi, then you can actually collect your omega many witnesses on the slices of a single class. And then the variant for second order set theory would say, instead of for every natural number n, for every set. Okay, so we have the choice scheme, and then we have the dependent choice scheme, which is exactly the axiom of dependent choices, but only for classes. So it says that if you have a relation on classes without terminal nodes, then you can make omega many dependent choices along this relation. Okay, so in second order arithmetic, full second order arithmetic Z2 with the choice scheme. So the choice scheme is stronger than second order arithmetic. And then if you include the choice scheme, then you get sigma 1, 2 dependent choice free. And then the question is, would be whether this is optimal. And so it's a theorem in Simpson's book that there is a model of second order, of full second order arithmetic with the choice scheme in which pi 1, 2 dependent choice scheme fails. Okay, so when I saw the theorem, I emailed Simpson, and he said that he thought that he had the proof of the theorem many years ago, but he has no recollection of the proof, and in fact, maybe he didn't even have the correct proof to begin with. So basically, it turned. According to him, this was not yet a theorem. So me and Sai set out to prove it. And what we did was we constructed a model satisfying the statement of the theorem as the reals of a symmetric submodel of a forcing extension by a tree iteration of Jensen's forcing. And I will tell you what a tree iteration is later. And so we submitted the paper. And the referee report came back, and it turns out that Canavier had proved this theorem many years earlier and published it in a Russian journal. And his construction wasn't exactly the same, but it was similar. It also used iterations. It used slightly different iterations of Jensen's force. So this ended up being a joint paper because of that. So that is the history of the result. And of course, the point was that now that we had the theorem, the idea was to generalize Jensen's forcing to get the result, which is what I originally wanted for Kelly-Morse. And that is the motivation for the generalization of Jensen's forcing that I at least have, that I'll talk about here. Okay. So before we get to the generalization, I want to remind people or tell people about how Jensen's forcing is constructed. And the construction that I give here is from a paper of Yuri Abraham. So this is not Jensen's. I don't think this is Jensen's original construction, but I like to work with this one more. Okay, so I need a bunch of ingredients here, and we'll start with the notion of a perfect poset. Okay, just a quick reminder, we say that a subtree of the full binary tree is perfect if every node has a splitting node above it. And one of the nice properties of perfect trees is if you have two perfect trees, T and S, and if their intersection contains a perfect tree, then in fact it contains a maximal perfect tree. And we'll call this the meet of T and S, denoted like this. So this is the standard meet. Okay, so I will use this notion of meets in my definition of what a perfect poset is. So a subposet of sex forcing is going to be called perfect if it contains the full binary tree restricted to every node. So what do I mean with the notation to the less than omega with this node S at the bottom? It means that we take the stem up to S and then everything above it. This is fairly standard, but I thought I would mention it. So it contains all of those, and then it's closed under unions and under meets. So closure under unions is going to be key in our construction. And then closure under meets is useful in many situations. One of them is that, for instance, if you have closure under meets, then incompatibility doesn't change as you expand the forcing. So if your two trees were incompatible in P, and if we expand P to some larger perfect forcing Q, then the conditions continue to be incompatible there. And it has other uses. So meets are extremely useful. Okay, so a standard proposition about perfect posets is that a generic for a perfect poset is determined by a real. And this is the same as for the full sex forcing. So the real is the cofinal branch, which is the intersection of all the trees in the generic, and then you can construct the generic from the real, because the generic is just all the trees in the poset which have this real as a cofinal branch. Okay, and a final thing I want to say here is that the smallest perfect poset is just you take all of these restrictions of the full binary tree and you close under unions. Here, I think the closure under meets is just free, so you don't have to do it. Okay, this was one ingredient. The next ingredient is this notion of a fusion poset for a perfect poset. Okay, so if I have a perfect poset P, the fusion poset, its elements, so I'm going to call it QP, and its elements are pairs Tn, where T is a tree in my poset and N is a natural number referring to a level of this tree, with the ordering that Tn is less than or equal to Sm, if they agree up to level M, and then you can thin out to T after that. So you agree up to level M, and then you can thin out. And so the fusion poset is sort of a nice way of expressing fusion arguments with the trees from T by meeting dense sets of this poset. So I don't think you actually need it, but I kind of like it as opposed to doing fusion arguments. It's more intuitive for me, and this is from Yuri Abraham's paper. Okay. All right, so what does the fusion poset actually adds? Well, a generic for it is a generic perfect tree, which is the union of all the sort of fixed initial segments of the trees and the conditions in the generic. So this is one key property. And another is that this generic perfect tree is a subtree of every tree mentioned in the conditions in the generic. And again, I will use the notation less than omega here to refer to a finite support omega length product of the QP. Okay. So what am I going to use the fusion poset for? We will use it for growing our perfect poset to a larger perfect poset. And here I will assume that I have a full generic for the fusion poset, but in the construction of Jensen forcing, we will force over countable models. So we'll have all our generics in the ground model. Okay, but here I am going to tell you how in a generic extension by the fusion poset to grow my perfect poset to a larger one. Okay, so here's our setup. I have a perfect poset P. I have that QP is the fusion poset, and I'm going to force with the omega length product. So I want to add omega many perfect trees. Now, omega many generic perfect trees. And then in the forcing extension, we will call P star the perfect poset, which is generated by all of my old trees in P together with these omega many generic trees. Generated, I mean close under meets and under unions. Okay. So, and like I said, in the construction of Jensen's forcing, we will do this over countable models to sort of grow our perfect posets into Jensen's forcing. So that's a hint of what is to come. Okay, so let's get some intuition for what conditions in P star looks like. What does a meet of one of these old trees with one of the generic ones look like? So I'm only doing two very simple proofs in this talk. And the intention of the proofs is to show you how we do arguments with these perfect trees and the fusion posets. And basically, a lot of the rest of the construction is going to be arguments that are very similar to the two proofs that I'm going to show you. So they're just here to be instructive. And they also show you where the properties of the perfect poset that I required actually get used. Okay. So let me have a drink of water before I do the proofs. And I apologize about my voice. I'm getting over a cold, so I do need to drink. Otherwise, I'm going to start coughing. Okay. All right. So if you have one of the old perfect trees and you take a meet with one of the generic ones, one of the nice properties that you have is that a chunk of the generic, okay, so if you take a meet, right, and it's a perfect tree, so the meet is a perfect tree. The meet, the way that you construct the meet is either it's a perfect tree or it's empty. Okay, that's what I mean by a meet is a perfect tree. And I think everybody knows you just construct the meet by just, you keep eliminating the nodes which don't split in the intersection. Okay, so if the meet is a perfect tree, then it turns out that the original old tree already contains a large chunk of the generic tree with which it has a meet. Namely, there is a node in the generic tree that it contains everything up to that node. And this is a very useful property of these posets. Okay, so I'm going to give a density argument to show that this is the case. Okay. All right, so we know that the meet is a perfect tree. So in particular, I can fix a node in this perfect tree. Let's call it T. And so there is some condition in the generic. And remember, the generic is for this forcing, okay? So there is some condition in the generic that forces that this node is in this meet with the generic tree on the nth coordinate. So I will do a density argument below this condition P. So let's fix any condition Q below P. And since we only care about the generic tree on the nth coordinate, we only care about the nth coordinate of the condition here. So let's specify what it is. So let's say that on the nth coordinate, we have the tree S and then level M. And by taking a slightly stronger condition Q, I can assume that the level M is above the level of this node T. And of course, because Q is below P and P forces that this node is in the tree, it must be that the node T is actually in S. So this picture that I have here is accurate. Okay. All right, so I have the node T because I'm working below P is in S, and I can assume by strengthening slightly that M is above, the level M is above the node T. Okay, we also know that since P forces that this is the case, then Q also forces that the meet is a perfect tree. Okay, now this perfect tree on the end coordinate has to be contained in, if Q is in the generic, then this tree has to be contained in S. So if this tree has a perfect meet with T, then of course S must as well. And in particular, this has to happen. There has to be some node on level N such that the meet of S and T is a perfect tree. Because if this wasn't the case, this could never be the case for the generic perfect tree. Okay, so on one of the nodes above T, it must be the case that the meet is a perfect tree. So I can thin out the tree above this node to whatever this meet U is. Okay, so I'm going to, and this should not say S prime, sorry, this should be S bar. I kept changing the notation and I messed that up. Okay, so S bar is the tree where I start with S. I keep everything the same, but on this one chosen node above T, I'm going to thin out to U. Okay, so I will ensure that this, the tree above here is going to be contained in T. And of course, if such a condition makes this into the generic, it will ensure that the generic tree will be contained in T as well, which was the desired result. Okay, I need to argue that this condition S bar is actually in my pose at P, because the pose at P isn't the full sex forcing, right? And for this, we use the union property. Because what is this tree S bar? It's the union of all of these. But all of these are in my perfect poset, and I have closure on their unions. And therefore, S bar is also in P. And so then I let Q bar be the condition where I replace S with S bar, and I leave everything else the same. And since I could strengthen any condition Q to such a condition Q bar, one of these must be in the generic. And I already said, if one of these is in the generic, then it achieves the desired result, that there is a node where the generic tree will be completely contained in T as desired. Okay, any questions about this proof before I move on? This is basically every argument about Jensen's forcing is a construction of this kind. All of them, essentially. You just pick a level and you thin out either the tree above one node on that level, or you thin out all of them. Okay, so now I can use the proposition that we just proved to prove one of the key properties that I want of this larger forcing. Okay, so the forcing P star has the following three key properties. One is that the restrictions of the generic trees to some node are dense in this new forcing. Two is that the trees themselves are a maximal anti-chain. And three is really the key property here. And that is that we have sealed every maximal anti-chain of P. And you can sort of see where this is going in terms of eventually getting the CCC in the construction of Jensen's forcing. Okay, so the first property is true by the proposition that I just showed. So this gives density, because really our trees in P star are just unions of these, right? Because we close under unions and means. So by this we have the density. Okay, so if I can show then that this is an anti-chain, then it will be maximal by 1. And it's an anti-chain because the density argument shows, unsurprisingly, that if you take generic trees from different coordinates, then their intersection is going to be bounded. So they're incompatible. They don't have a perfect tree in their intersection. Okay, so the last thing to prove is 3, and this is the only other proof that I am doing, and you can see the same picture on the slide because, well, it's going to be pretty much the same argument, just as I promised. Okay, so we want to argue that we have sealed maximal antichains from P. So let's fix a maximal antichain script TA of P from V, and and because we have already showed density, it suffices to show that every one of these trees is compatible with an element of my anti-chain. Okay? So let's fix one such tree. And again, let's work below a condition that forces that this node T is in the generic tree. Okay. All right, so it's a very similar density argument. So we will let's fix a condition below P. And again, by strengthening slightly, I can assume that the level M here is above the chosen node T. And T is in it because I'm working below P. And we will choose now any node S above T. Okay, in this condition. So we don't need to worry about which one it is. We just need to pick one. And so the tree S restricted to this node, because script A is a maximal anti-chain, is compatible with some element A in the anti-chain script A. So I can pick a tree U below both of them, and I'm going to thin out to U. What that is going to ensure is that if a condition of this kind ends up in the generic, then the generic tree restricted to this node will be below an element of my anti-chain, because it has to, of course, be a thinning out of S little s. Okay, but since these conditions are dense, one of them has to end up in the generic, and therefore we have verified our sealing maximal anti-chains property. I need a final ingredient before I show you the construction of Jensen's forcing. Okay, how am I doing on time? Okay. So for this construction, I will be working in L, and I will be using a particular diamond sequence, a particular fixed diamond sequence. In the construction here, you don't really need to work in L, and you can work with any diamond sequence. It makes the construction a little bit more complicated. So this is why I went with sort of the simplest one. So we will work in L, and we'll fix the canonical diamond sequence. So what is the canonical diamond sequence? This is the one defined in Yak's book, where you take the least counter example if it exists, the L least counter example if it exists, as you're building the sequence. And I'll tell you why we need the canonical one in a second, why it makes things simpler. Okay, so here's the last ingredient. It's a notion of a suitable model M. So now a suitable model M is a countable L alpha, which satisfies ZFC without power set, but I want the power set of omega to exist. So I don't need the power set of, say, omega 1 to exist, but I need the power set of omega to exist. Okay, sort of the easiest examples of such models is take a countable elementary substructure of L omega 2 and collapse it. So that will satisfy all of the properties. And these are the ones that we work with in the construction, basically. And so one of the sort of key nice properties of suitable models is that they're correct about the canonical diamond sequence. So if you have a suitable model and delta is the omega 1 of this model, then it has the sequence up to delta, and it knows that it's the canonical sequence. Okay, so finally, here's the construction of Jensen's forcing, or at least the sketch of the construction. Okay, so we will build Jensen's forcing as the union of a chain of length omega-1 of perfect posets. We will start with the smallest perfect poset P min. At limit stages, we will simply take unions. So the interesting thing here is going to happen at successor stages, and this is where we will use diamond. So suppose we have constructed peak C. We look at the xth element of our canonical diamond sequence. If it happens to code a suitable model, call it MXC, such that it has peak C as an element and its omega-1 is Xc, then we will force over MXC with the fusion poset for peak C, adding some omega many MXC generic trees. And we will let the next stage poset be the peak C star as constructed in this generic extension, and we will use the L least generic of course, this is a countable model, so I have plenty of generics. And as you can imagine, I am not giving a proof of this, but as you can imagine, and it's not difficult to prove anyway with the information that we already have. But from the property that I showed you, it will turn out to be the case that every maximal anti-chain of peak C from MXC gets sealed. So it will remain maximal NJ, and this is what's going to give you this CCC. Okay, so diamond plays a role actually in both the CCC and the uniqueness, but okay. So we can use, as I already mentioned, you can use different diamond sequences. It doesn't need to be the canonical one. That of course is going to give different models MXC. But the construction becomes, you sort of need to add something into the construction. It still works. You keep the CCC and the uniqueness of generics, but you will lose the low complexity of the generic if you do that. Okay. So since I mentioned iterations and finite iterations and tree iterations, let me just tell you what they are a little bit. Okay, so how would you iterate Jensen's forcing? Well, as I said, in order to construct a Jensen's forcing, you just need diamond. Jensen's forcing is CCC. CCC preserves diamond. So in a forcing extension by Jensen's forcing, you do have diamond. So you have Jensen's forcings there. So the iteration does make sense, first of all. But in order to achieve uniqueness property, you have to be, at least I don't know if it will work otherwise, the way that you do it is you have to be careful about the kind of the diamond sequence that you use, meaning, and the kind of models that you use. So the way that you build the Jensen forcing in the extension is you use extensions of ground models MXC given by diamond in the ground. Okay, so you kind of have to be, it's not completely straightforward, but it works. Okay, so our tree iterations are iterations along a tree of height omega. And this is what the poset looks like. So given a tree scripted T of height omega, the Jensen iteration along T, its conditions are functions whose domain is a finite subtree of scripted T, such that on a node of the tree T on level N, I put conditions from Jn, the nth iteration, okay? And we do it coherently. So if I put a condition on level 3, the conditions below it as just the restrictions of this condition. So what object does such a forcing add? Well, it adds a tree isomorphic to the original tree T, whose nodes are generics, whose nodes on level n are generics for Jn. So it adds a tree of generics for finite iterations that are coherent. Okay, and what we showed with psi is in a forcing extension by such a tree forcing, the only generics for the finite iterations are the ones coming from the nodes of the tree. So this is another uniqueness of generics property, and it's a corollary of this that finite iterates have unique generics. Okay, so this finishes the first part. So now I will talk about the actual generalization. Any questions before I move on? Okay, good. Okay, so the issues that came up in generalizing Jensen's forcing to an inaccessible kappa were as follows. Okay, so here you have to work obviously with perfect kappa trees. And the problem is perfect kappa trees are just not as nicely behaved as perfect trees because of limit levels. This is to be expected. So you don't have meets. You don't have the right closure under union. So think of, let's go back to this argument. In order to argue that this condition was in the perfect poset, we needed to take a finite union over these trees. Well, if it's a kappa tree, we will need to take a less than kappa size union. But perfect trees are just not perfect kappa trees are not closed under such unions. The other issue, so these were the two sort of more resolvable issue. The bigger issue was the following. Okay, in order to be useful, the generalized Jensen forcing needed to be less than kappa closed. So now think of the construction again of Jensen's forcing. We take, at limit, if we want to generalize the construction, it would have to be built in kappa plus many steps. But to ensure closure, we would have a problem if we take unions at limits of cofinality less than kappa, because at those we would break closure. So at limits of cofinality less than kappa in the same construction, we would need to close up under less than kappa sequences. But at the same time, we're trying to seal maximal anti-chains. So if you do this additional closing up, the question was, will this unseal maximal anti-chains? And it somehow miraculously turned out that you don't. And this was sort of Psi's brilliant insight. I at that point thought that the whole thing would not work. I'm not an optimist. Okay. So now let's start talking about what are the ingredients here and everything. You will see that we're generalizing a lot of this stuff, and then you will see where things are different as well. So first, let me recall the definition of perfect kappa trees, because it's sort of, it has subtleties. Okay, so throughout kappa is inaccessible. So a perfect kappa tree is a subtree of 2 to the less than kappa that has size kappa, so it's a kappa tree. Every node has a splitting node above it, so it's splitting. If you have nodes up to a limit level, you have to put a node on the limit level, so T is closed. And if your nodes split cofinally before a limit level, you have to split at the limit level. So when you're thinning out a perfect kappa tree, you have to be very careful, really not to thin out at limit levels, because you might lose the splitting property. It presents issues. So we always, when we're thinning out, we always work with successor levels. We'll always work with successor levels. Okay, and a standard fact about these perfect kappa trees is that they're closed under intersections of length less than kappa. So if you have a decreasing sequence of perfect kappa trees of length less than kappa, then its intersection is a perfect kappa tree. This is sort of the standard fact. Okay, and as I already mentioned, perfect kappa trees don't have the two nice properties that we were using before. So there are perfect trees that have perfect trees in the intersection, but have no maximal such tree. It's easy to construct the counterexample. And they're not closed even under omega unions. So we will have to modify the construction that we had before. We will have to modify the definition of a perfect poset. So here's the definition of a kappa perfect poset. Okay, so it's a collection of perfect kappa trees. It has the full tree. Whenever it has a tree restricted to some node. If you have a descending sequence of trees in the poset of length less than kappa, then you have the intersection as well. So I want to have all of my intersections already in P. It helps a lot. And we call this the less than kappa closure property. And then we need to do something about unions, because remember, unions were absolutely crucial to the arguments here. So we don't have unions. Instead, we're going to replace this with the weak union property. So think about what we really, and the weak union property is going to be sort of the bare minimum of what we needed to get the constructions and the proofs that I showed you to run, okay? So that was that if I have a tree in the poset and I restrict it to some level, I can thin out all of the trees on that level, and then the union of this is again a tree in my poset. So that's exactly what weak union property says. It says that I can do this. So it says that if I have a tree in the poset and each of these red trees are in my poset, then the union is in the poset. So, but I can only do this on a fixed level. And this kind of weak union property we can have. And it turns out this is exactly what we need for the construction. So we isolated this as the property that was really necessary to run the construction. Okay, so kappa perfect posets have the property that the generic is determined in the same way by a subset of kappa. And the smallest kappa perfect poset, I will again call it P min, is just you start with the full trees restricted to some node and you close under less than kappa intersection and the weak union property. And of course, because both are about objects of length less than kappa, you can close in kappa many steps. You can close up in kappa many steps. So you do the obvious thing. You start with whatever trees that you start with. We will do this construction for kappa many steps. You take unions at limits, and its successors you close under the two properties. And the final result is going to be P min. Obviously, this is the minimum of what you have to do, so it will give you the smallest one. Okay. So if you start playing around with this, you're like, what do elements in this poset actually look like? And you can spend some time trying to figure out what these things look like because of these two closure properties. But the nice thing is, it really doesn't matter. So I call this the clean levels lamp. And what it says is, if you have a tree in this poset, as long as you go to some high enough level, it actually looks like the full tree. You might have some mess on the bottom here, but as long as you go high enough up, you know exactly what your elements look like. They really look like just like the full tree. Okay. And so we will have more of these clean level lemmas. Okay, so first let's get an analog of the fusion poset as well. So here the conditions are going to be the tree T and some ordinal alpha, which refers to the level of the tree. And as I said, I don't want to work with the limit levels because I can lose the perfect tree property there. So we work with successor levels. Oh, and I should have mentioned here, sorry. Here I take a successor level again, because otherwise you won't get get the property, because you might lose splitting. So you really want to work at successor levels everywhere here. Okay, where was I? Okay. All right, so it's defined, the fusion poset is defined completely analogously. It's less than kappa closed. It adds a perfect kappa tree that is contained in every tree in conditions in the generic. And here we will want to work with bounded support kappa length product. This is the generalization from the omega length product. Okay. All right, so our setup is the same as before, essentially. The setup is, the setup is that we want to now grow our kappa perfect poset P to this larger poset P star as before. Okay, so we start with the kappa perfect poset P. We have a fusion poset. We force with the kappa length product of it to add a kappa many generic trees. And our poset P star is going to be in the forcing extension, the closure of P with these generic trees under less than kappa intersection and the weak union property. So this is, again, you just do the same closure in kappa many steps that we did to obtain P min. Okay. And again, the question is, what do elements of P star look like? And we have another nice clean levels left. So if you have a tree in P star, as long as you go to a high enough level, if you look at any given node, the tree that sits above that node is either one of the generic trees or it's one of the old trees. So as long as you're working above a large enough node, we know exactly what the elements of our P star look like. And this is super useful in actually working in construction space. Okay, so the clean levels lemma immediately gives us that the trees, that the generic trees are dense. So this is a maximal anti-chain. And essentially the same argument as the one that I showed you before shows that you seal maximal anti-chains. Because of the weak union property, you can do exactly the same construction. Okay, so kappa suitable models. This is the last thing that we need to generalize. And again, for simplicity, we will work in L, and we need to fix a diamond kappa plus cove kappa sequence. So we need, because we will need closure everywhere, this is the reason we need to work with the cove kappa sequence. Okay, so what is a kappa suitable model? It's an alpha of size kappa that satisfies ZFC minus, but power set of kappa should exist. It doesn't need to have larger ones. And we want it to be closed under less than kappa sequences. And there are many reasons to want closure, but we will see one of them in a second. Okay, so again, what are examples of these models? You just take elementary substructures of L kappa double plus that are closed and have size kappa, and you collapse them. Okay, and again, you have the key property that these models are correct about the diamond sequence. And remember, what did we need to do in the construction? We need to force over these, right? But of course, this is a model of size. This is a model of size kappa now. This is not a countable model, but because of closure, we actually have generics. So if you have a kappa size model that is less than kappa closed, you can build generic filters for it. You just do the usual diagonalization argument and you use closure to get through limit stages. And the poset has to be less than kappa closed, of course. I should have put that in. So I need the poset is an M and the poset is O. I mean, I'm assuming here, am I assuming that P is a perfect poset? I guess. The poset needs to be less than kappa closed, and then you can build generics. Okay. All right, so here's our construction. So it basically proceeds as before with one exception. So we will build the generalized Jensen's forcing. It's a union of a chain of length kappa plus of kappa perfect posets. we start with P min at the bottom. At successor stages, we do exactly the same thing that we did in Jensen's forcing. At stages of cofinality, kappa, at limit stages of cofinality, kappa, we take unions. And if you have, if you're at a limit stage of cofinality less than kappa, you take the union and then you close under less than kappa intersection and the weak union property doing this kappa stage construction, the same way that we close always. And you can do an argument to show that you don't unseal maximal anti-chains. I didn't expect it to be the case, but everything does work out, even though it seems that you're doing these extra closure steps. Okay, so for the next slide, so we are doing this for kappa plus many stages, and in each of the stages, in each of the good stages given by the diamond sequence, we add all of these generic trees. Okay, so this will denote generic trees added at stage C. So script T upper C denotes the tree. Script T upper C denotes the tree added at stage at one of the non-trivial stages C, because I want to refer to them on this slide. And I have my final sort of really nice clean levels left. So what do trees in the generalized Jensen forcing really look like? Again, if I go to a high enough level and I restrict to some node, I know exactly what my tree looks like. So either it's the full tree, or it's one of the generic trees added along the way, or it's an intersection of a decreasing sequence of the generic trees. So it's sort of exactly kind of the minimal stuff that needed to be there. In this case comes from this closure. And we get the sealing lemma, which is the one that we were really worried about initially, that you do seal maximal anti-chains from MC. And so this generalized forcing has all of the properties which we wanted it to have. It's less than kappa closed. It has the kappa plus CC. It adds a unique generic subset of kappa. We get the unique generics property for bounded support kappa length product. So if you force with the bounded support kappa length product of the generalized Jensen's forcing, then the only generics for it are the ones coming from the slices of the generic filter, the kappa many slices. You get the generics property for the tree iteration of trees of height omega. So it is the same as before. So if you do the same iteration over a tree of height omega, then for the finite iterations, the only generics that you've added are the ones on the nodes of the generic tree. We don't really know. I don't think we've ever looked at what happens beyond finite iterations. And so as a corollary of this, you get uniqueness of generics for finite iterations. And I think all of this works, although it's extremely technical, and I am on hopefully my last sort of draft of the paper. And so I think we have this theorem. I say almost because I don't want to say it until I have the final draft, because I mean, the technical stuff is a total mess. But I think we can show, everything generalizes to show that we have the thing that I wanted so many years back, and that's a model of Kelly-Morse with the choice scheme in which dependent choice scheme fails. And it's going to be the V kappa plus 1 of a symmetric submodel of a forcing extension by a tree iteration of the generalized Jensen forcing. And so this is my last slide. I forgot the thank you slide.
Thank you very much. Very nice talk. So can I just ask, a question. So, I mean, the way I have, the way I understand Jensen's forcing in a way, I mean, there's a super close relationship between it and Suslin trees, it seems, right? It's like the construction is kind of the same way. You build
Right.
an omega-1 Suslin tree, but you end up with a forcing that adds reals. So somehow magically you're able to basically, in a way, compress an omega-1 Suslin tree into this perfect tree forcing or something like that, right? In a way. And now thinking about the generalization to kappa, the construction looks like taking a basically similar to the construction of a kappa plus Suslin tree and, doing a similar thing. Like it's even the same assumption, usually, a diamond kappa plus of Cove kappa sequence. And so I wonder, but in that situation, so to speak, the main motivation is missing, namely, there are no omega Suslin trees. So that makes sense then to try to take an omega-1 Suslin tree and compress it into something that adds a subset of omega. While at kappa, at least working in L, if kappa is not weakly compact, then you have a kappa Suslin tree. So I guess my question then is, like, what can you do with this forcing that you can't do with an adequate kappa Suslin tree, say? Like, for example, if you want to add a unique generic subset of kappa, that can be done with a rigid kappa Suslin tree. Or if you want to add exactly kappa many generic objects, if you take an adequately homogeneous kappa Suslin tree, I think that can also be arranged. Is it the iteration, like iterating it, or anyway? So this is my question.
So I never thought about it in that way. So your question is, would this construction just run? So we need uniqueness for iterations, definitely.
Right. Yeah.
I mean, that is absolutely crucial. And in fact,
yeah, I mean, okay, so
for
there
the
are, I
tree
guess,
iterations.
yeah, so I'm not sure. Okay, so there are these Suslin trees where you can repeatedly force with the same tree and add exactly one new branch.
True. Yeah, so Gunther, I didn't think about it. It might,
okay.
I mean, it's worth thinking about. It might, so my application in mind has always been basically the Kelly-Morse result. And
Right.
that was the only construction to get there. And it's not really using anything about the forcing. I mean, I don't.
Okay, because like, I mean, I think it's great. It's just, so to speak, yeah, I mean, maybe I'm looking at it the wrong way, but so if you think about it abstractly, like I said, the thing that you can do this way, that you couldn't do with a Suslin tree would be in the case that there are no kappa Suslin trees, right? So if kappa is weakly compact, for example, and you still have this forcing that would be able to do that. Right. So that's something you couldn't replicate with Suslin trees in a sense, I guess. But yeah, I guess, I mean, there are so many technicalities in the final application, so that I have no idea how far.
I don't know. I mean, I have to think about it. Right now, I think uniqueness is. I have to think about it.
Okay. All right.
No, I think it might be. I have to think about it, Gunther. Okay. And you're saying that we can get. Yeah, I mean, the technicality is in getting the uniqueness property for this tree iteration.
Right.
Yeah, which is fairly complicated and coming out of the construction of the post set.
Yeah, I think that's probably where.
Yeah, so will that, I don't know.
Yeah, okay. Okay.
Whether it, yeah.
Cool. Yeah, sorry for this longish question.
No. I've never actually thought about it in that way. That is really interesting.
Okay. Could I ask a very basic? I think I just missed a hypothesis somewhere. So that somewhere around the middle of the talk was CCC forcing preserves diamond?
I was
Yeah.
going to ask that question also.
Yeah, what did I miss?
Page 14.
Because add a zillion Cohen wheels,
Yes,
ruin
yes.
CH, therefore you've ruined diamond.
Yes,
Page
What-
14.
I missed
Page
that one. Okay.
14. It's
Yeah, you
page
can blow up the
14.
continuum and definitely kill diamond that way. Yeah.
Okay, so what did I want to say? I thought CCC forcing preserved diamond. Is that
Page
just
14.
blatantly false? Hmm?
You
Yes.
can destroy the CH by adding by CCC force.
Oh yeah, I'm stupid. No, you can't. It can be. So what is the is there some sort of
Yeah, by countable CCC forcing. And
Yes.
similarly, if you have a diamond kappa and you force with kappa CC
okay? Yeah, no, this is
forcing of
stupid,
size
sorry.
kappa.
Yeah, yeah. No, this is stupid. Sorry. Yes, of course, obviously. Yeah, that's
Or I guess
obvious. false, yeah.
CCC forcing of size omega-1 should also be fine, right? I think.
I think so. Yeah. Yeah. No, it has to have. No, I think it is omega-1. That's what I. Yeah, of course it can't. That's
Oh,
ridiculous.
that sounds
Okay,
good.
never mind. Yes. Yeah.
Okay,
Yeah.
so-
Absolutely. Yes.
Okay, good, thank you.
Yeah, I really need to correct that before I post the slides. That's terrible.
Any more questions or comments? Okay, I think we're all happy. Thank you again for the very nice talk.
Thanks, Vika. And we have on next week, we have Sakai, who is staying up very late to give us a talk. So we should
But
all
he's-
make sure to be there. I think it's close to midnight for him.
And we start early, right?
And we start early. Yes, we're starting at 11. It's 11 a.m., right?
I think so, yes. That's what we
Okay, yeah, because just so it's a little bit earlier for him. So I hope that he gets a good audience for his trouble.
Okay.
Yeah, and it looks like a really interesting talk actually from the abstract. That's good.